small.
Okay.
So it's a more regional one. Sorry for keeping you up.
Oh, no, you're fine.
A lot of fun.
Okay, so
Yeah.
6, 8, 8.
Yeah, it's really small.
Awesome.
I mean,
Yeah, and like I said, I'm.
Thank you.
That's cool.
I like the floor.
yeah.
Rebuild is like
Welcome, everybody. Go ahead and give me one of the lights. How's that? You want to do it that way, or?
I think last time they had it, yeah, just the back.
Okay, welcome all. Thanks for joining us this afternoon. My name is Judy Beck, and I'm in the Department of Physics here at UNC Asheville. And I'd like to introduce our next speaker, Nathan Kirse from the University of North Carolina, Asheville.
All right, so I did my project on exoplanets, and what I'm doing is a search for KOIs. So first things first, what is an exoplanet? An exoplanet is quite simply just a planet that orbits a star other than our own. And how do we find exoplanets? There's many ways that astronomers detect exoplanets. The way I'm using is known as the transit method. Now the transit method simply utilizes the periodic eclipse between a planet and the star that it's orbiting, its parent star. So the planet just passes in front of the star and blocks a little bit of that star's light, making it that star appear to dim. Now it's important to understand that this method only works for a handful of exoplanets. So the inclination of the orbit has to go through the star. So like the planets on the top will transit its star because it's moving across the face of its star, but the ones on the bottom will not. Okay. So the biggest contributor to the discovery of exoplanets is the Kepler mission, the Kepler Space Telescope. And so far, astronomers have discovered almost 2,000 exoplanets. And there's almost 5,000 unconfirmed exoplanets. Now, these unconfirmed exoplanets are what I'm looking at. And an unconfirmed exoplanet is also known as a KOI, that stands for Kepler Object of Interest. And what I want to do is I want to find a target KOI and just observe it and try to detect a transit. And in doing so, hopefully help it become a confirmed exoplanet and not just an unconfirmed. It's not just a KOI. Right? So if I wanted to have any hope of doing this, I was going to have to find a pretty good telescope, better than what UNCA had to offer. So I got my hands on the Sierra Stars Observatory. It's located east of the Sierra Nevada mountains in California. And it's a fairly large telescope. It has an aperture of about 2 feet, so the mirror on it is about 2 feet wide. But the most important thing is its location. It's in a pretty arid and very dark location, so it's a pretty good site for doing optical astronomy. So I didn't know how good this telescope was going to be, so I was going to just try to find the hardest target and the most interesting target. And that was the most Earth-like planets. So what you see here is a list of the most Earth-like exoplanets discovered or unconfirmed so far. And the one that happened to work out is this one right here, KOI 2418.01. So again, this is Earth-like exoplanet. It's similar in size to the Earth, and it orbits in a region around the star where it is possible that water could exist on the surface of this planet. So its radius is only 10% larger than Earth, and it orbits a fairly small star. It's the star that it orbits is only a fourth the size of the sun. Alright, now the sky was supposed to be clear for the time that the planet transited its star, but unfortunately a fire happened somewhere north of the observatory, and that dramatically changed the weather conditions. So my chance at detecting this Earthlike exoplanet was gone. So I did the only thing I could do, and I had to find another one. So I ended up on this KOI. It's a lot larger than the last one. This one has a radius about 3 times that of Earth's. And its star is also, its star that it orbits, or no, the star that the planet orbits is about the size of the sun. And it orbits its star in 48 days. And then at the bottom right, the middle planet is a size comparison of, the middle planet is the KOI, that's just a size comparison of the planet with planets in our solar system. So, fortunately, the sky was clear for this one, and I was able to take images. So basically what I did was I just pointed the telescope at the star, and I took images about every other minute for 4 hours. And once I got the images back, I'm able to do differential photometry. And basically how this works is that it just measures the change in brightness of the star by comparing the target star to comparison stars in the same field of view. So for this I used Astro Image J, and this is an actual image this is an image that I have pulled up in Astro Image J. Now, quite simply what I do is just I put the circular cursor on top of the target star. Now that T1 is the star that KOI orbits, okay? Now when I put the cursor over the target star, I get what's called the integrated counts. Now I'm not going to go into explaining what integrated counts are, but you can just think of it as the brightness of the star, okay? So I get that value, and I also get the brightnesses of the comparison stars, which are labeled in red. So I have 3 comparison stars for this one. Now, so basically what I'm doing, I'm getting a ratio between the target star and the comparison stars for every single image. All like 200 images that was taken that night. And I put it on a graph. So you can think of the y-axis as the brightness of my target star, and the x-axis as just time. So as you can see, it's just straight across. Now what I wanted to see was a nice dip in brightness, but that was not seen at all. And the reason for that is probably just because the amount that the planet dimmed its star was just much too little for the camera to pick up. All right. So I chose another target, and I chose a much bigger planet because the bigger the planet, the bigger the change in brightness, because it's blocking more of its star. So this one has this planet has a radius 9.35 times that of Earth's, so it's much, much bigger. And it also orbits its star in just 1 day. So 1 year on this planet is a year on this planet is 1 day long. So it's going around really fast. And it has a temperature probably comparable to that of Venus, since it's so close to its star. Here's a size comparison. As you can see, it's about the size of Saturn. And its star is fairly small. It's what you would call a red dwarf star. Now, skies were clear, and I was able to get 5 hours of observing in. We got hundreds of images back. And I did the same thing. I did differential photometry, just taking the ratio of the target star and the comparison star, and doing that for every image. And this is the plot that I got back. Again, the y-axis is brightness and x-axis is time. So something is going on here. It's not a flat line as it was before. So, but it's still not like, it doesn't look like a transit. There's like 3 like different spikes. So something is going on here, but it's not a transit. So, and by the way, in the upper right corner is like the comparison stars I'm using in red, and then the green circle is my target star. Okay. Now the first thing you do when you get something crazy like this is you check your comparison stars to see what they're doing. Because the perfect comparison star is a star that doesn't change in brightness at all throughout time. Okay? So if your comparison stars are changing in brightness, then that's going to mess up your data. And the first comparison star I checked was doing having some big changes in brightness. All right, and it was indeed contributing to my messed up results. So what I did, I went through and took away some bad comparison stars. So now I'm just left with 4 comparison stars, those red circles in the top right. And now I'm getting something that looks a little bit like a transit. It's not too confirming, but so what I did now is I just went back through and took a few more comparison stars out. And now we're getting nice parabolic transit shape. Okay? So I couldn't really take any more comparison stars away since I only have 2 now. So I was satisfied with this, and as you can see, there is a very obvious change in brightness. And the ingress is when the planet is moving, just moving in front of its star, and the egress is when the planet is leaving. Okay. So once you do, what you do when you get something like this, in order to verify that you did indeed detect a transit, is you have to make sure that these the fluctuations downward were not just like a random. It wasn't just randomness that that change of brightness happened. All right. So I'm not going to talk about this too much, but if you've taken stat, the error between the ingress and egress was just rounds up to 7 sigma. So basically this means that I did detect a transit. It was not just a random event. All right. So what can we learn from this data? So I'm just comparing what I had to Kepler data. So the transit midpoint lines up with what the Kepler telescope has. The transit duration does not. The transit duration is just how long the transit was. And the reason that probably doesn't match up is because the camera that NASA put on the Kepler Space Telescope was probably a lot more sensitive and was able to detect a much larger portion of the transit. All right, the transit depth matched up. The planetary radius matches up with what Kepler has. And the star luminosity was given to me. And what I did, I used this equation to estimate the distance of this star. And so I estimated this distance, this star to be about 460 light years away. So that means that the night that I detected this transit actually occurred 460 years ago, because a light year is the distance that light travels in 1 year. All right. Now that might sound like very far away. 460 light years might sound really far away, but in actuality, if the sun was at the center of that green circle, that KOI would still be within that green circle. So this planet is like within our galactic zip code. All right. So thank you all for coming. I would gladly take any questions.
theory on what was happening to your, the other stars, that was causing?
Like my comparison star?
Yeah, like one that was messing everything up. Do you
Yeah,
have a
that-
theory on why it was doing that?
At first, this kind of looked like an eclipsing binary. So the eclipsing binary is just two stars that are orbiting each other really close.
Okay.
They can like eclipse each other, and that kind of looked like that. But this is a much too small of a time period for that. So I don't know. Maybe it's eclipsing binary, but it's probably not. I don't know. Yeah.
Right, 2 questions. First of all, in terms of getting your telescope time, was it a collaboration? Did you just have to ask nice, or was there, you have to win time?
Well, you can apply for time, but the main reason was that I'm friends, or one of my relatives one of my relatives is a professor of astronomy at another university, and he has his students use this observatory. So he knows Rich Williams, who is in charge of the Sierra Stars Observatory. So he connected me to Rich.
Well, that's nice. You said the duration didn't quite match up. You didn't give an indication of how off it was.
Oh, so I think
I think your duration was a little over an hour.
yeah. So the duration was supposed to be like an hour and a half.
Well, that's not so bad.
Yeah, it's not too bad, but yeah. So like the reason I think that might be off is because there's a good room for error, here. And if you had a more because of noise. So if you had a more sensitive camera, these edges might become a little bit more fine. So that's what I was trying to say. Yeah.
Can you talk a little bit about the before transit and after transit? It seems that difference is way bigger even than the during transit difference. I'm wondering what's causing such a big difference.
So you're talking about this?
Yeah.
Oh,
Yeah.
okay, so I was doing these observations in, I think it was October, maybe. But by that point, Cygnus is the constellation that all of this is happening in. So by that point, Cygnus is getting pretty low in the sky. So Cygnus is pretty much on the horizon when it got to here. So that, just since it was really low on the horizon, going through all that air mass, that's probably why you're seeing all these fluctuations. Okay.
So how large would
Does
your
that answer
error,
your question?
sorry.
Does that make sense? Like,
I guess I'm just wondering because you're doing comparisons, right? They're ratios. So even
Yeah.
if that is true, the star you're comparing it to, that's also happening too.
yeah, that is true, but I don't know. I mean, yeah.
But they're getting dimmer, so each one has more noise.
You went to a larger air mass.
I think it's just, I don't know, atmospheric turbulence when you're getting that low in the sky, that nothing good. It's not a good place to do optical astronomy right above the horizon. So, any other questions? Yeah.
So you said as you have these comparison stars, do you have to select them before you do your data? Or
No.
can you go back to your images and then pick new comparison stars?
I select my comparison stars once I get the images, I literally just choose random stars and hope they work out. If you have a large enough field of view, you can go on a website, specifically AAVSO, and actually look up good comparison stars. But there were no comparison stars in my field of view, so I just had to pick random stars. Now for just a 5-hour period, most stars are relatively stable, but still sometimes that's not true, as you can see here. So yeah, so I just choose random stars for my comparison stars.
We have time for one more question.
On the plot you had, I think, 2 slides after this one. How large would your error bars be? Or are they already on there?
Yeah, no, I didn't put the error bars on there. I don't know. There's the error and change in average. Yeah, no, the error is just a standard deviation divided by the square root of the sample size. But no, I don't, my error isn't that big. I mean, the statistics like accounts for all of that. I mean, if the error bars grew really big, I wouldn't have gotten, you know, a 6 or 7 sigma down there. So transit didn't happen. The error bars weren't too